Bismillahirrahmanirrahim. Assalamu alaikum everyone. I am Dr. Abdullah M, and today I will be presenting on the topic of digital twin with UAVs. Okay, so these are the contents of our today's presentation. We'll first go ahead and look to the detail of what is this digital twin and what are the UAVs and how these are integrated with each other, and what are the application areas where these can be used. And then we'll see some case study that will give you a much better and deeper idea of what this digital twin technology is and how it can be used with the UAVs, which is the unmanned aerial vehicles. And then we'll in the end talk about some of the challenges and limitations and how these things can be applied to futuristic technologies. Okay, so let's dive into it. Okay, so let's start with the digital twin technology. So, well, basically, the digital twin is a virtual representation of a physical system. As the name suggests, well, for example, if we had a real life aeroplane in air or wheresoever, or it could be any other real life system, what we can do is we can use some techniques to represent it in a digital form, meaning that we can make a model in a computer that exactly replicates and mimics the behavior of a real life system. So that way we can do analysis and we can do a lot of experiments on our system without requiring the actual physical system. So it is the visual representation of a physical system. The physical system could be of any category. It could be from biomedical engineering, it could be from mechanical, civil, or it could be anything, any type of physical system. So it has real-time synchronization of data. So the main crux of digital twin is that while we used to have simulation models, which were also a digital representation of any physical system, but the real core part of digital twin is this real-time synchronization of data. That indicates that if your system is real-time changing due to whatsoever the reason, for example, in the case of this aeroplane, let's say due to whatsoever the reason, this one engine of the aeroplane failed. Well, now our model that we created using digital twin technology will also immediately show you that this engine has failed, and now the resultant analysis and the output results of what is going to happen can be simulated and can be shown in your computer in no time. Okay, so we can get real-time synchronization of data using this digital twin technology, and it enables us for simulation analysis and prediction of how our system is going to perform. Okay, so this is the basic introduction of what this digital twin technology is. So if we talk about how this digital twin can be helpful for UAV systems, which is the unmanned aerial vehicles, while it can accelerate their development cycles, it can enhance operational efficiency and safety, and we can use artificial intelligence, machine learning, along with digital twin for advanced autonomous missions. We'll see a case study later on where we'll go to the detail of and see how digital twin with UAVs can be used for enhanced efficiency and safety of the system, and how we can use it for acceleration and development of cycles. So moving on. So if we talk about the UAVs, well, these are the unmanned aerial vehicles. Most probably, if you have taken any of my previous classes, you already are familiar with this UAVs. For the newcomers, I'll just go ahead and again go to this slide. So there are different types of UAVs. Well, these are the category. This is the UAVs are the subcategory of this broader term, the unmanned vehicles. Okay, So there are ground vehicles, there are water vehicles, and then there are aerial vehicles. So today we are talking about these aerial vehicles. Even though the digital twin technology can be used with ground vehicles, water vehicles, surface vehicles, or even any other type of physical system. Okay. So in this UAV systems, we'll be doing a case study on this multi-copter domain, specifically this quadcopter. So in this UAV, there are fixed wings, there are flapping birds, flapping wings, mimicking the behavior of any birds. And then we have these multi-copters, which are the small drones. Okay, and then there are other configurations and so on. So there are fixed wing, rotary wing, and hybrid. This is fixed wing, and this multi-copter is your rotary wing. And we have sometimes the combination of these two together as well. It has wings as well, and propellers, motors, fans as well. So, well, we can use these UAVs for surveillance, delivery, mapping, disaster management, and much more. Well, the challenges we face in UAVs include the reliability, autonomy, and multi-domain operations. So well, there are a lot of different kinds of operations that you can perform using UAVs, and each type of task arise a specific type of challenge. So we need to design some theories and technologies in such a way that they provide a solution for a very diverse type of problems that we may face in operating the UAVs for multiple scenarios. Okay, so that was a brief introduction of what UAVs are. Now we'll go back to the digital twin technology and we'll see how it works. So, well, the core components of our digital twin technology include real-time data acquisition from our physical system. You have some system, what you will do is you will install some sensors on each part of it, and then you need to get data from your actual system for the digital twin to work. Okay, because we saw that digital twin can give you information in real time about your actual system. So logically, we need to put some sensors and get the data from the actual system to get the information. Then we can simulate it, right? So once we have this data, what we can do is we can do predictive analysis and we can test in virtual environments without any cost. Okay. So how do we get this real-time data acquisition? For example, the part one could be mathematical modeling of your physical system. Okay, so this includes the mathematical modeling, which has different kinds of methods. We'll not go to the detail of this. This is the most important part, the sensor selection. Once we have the equations that represent some physical system, now what we do is we put some sensors to our physical system and we incorporate it in mathematical equations as well. And then we get the data of these multiple sensors from our physical system and we will use some 3D modeling, for example, the SolidWorks software, and we'll feed all of that data to our software. So using that mathematical equations and these data, real-time data from our actual system, well, we design a 3D model that represents our actual system in real time. And once we have this 3D model, well, we can use simulations and we can perform virtual testing and we can predict and get any type of output that we want and can perform different types of experiments. So ultimately, we get this digital twin model. So basically, the crux is you had a simulated model, you installed some sensors to your physical systems, you got real-time data, and you updated your previously simulated model based on the real-time information from your physical system. So this way, a digital twin of your actual system was created with great precision and accuracy. And using this digital twin, you can do a lot of stuff and predict how your system is going to behave if you do some specific actions. So what are the advantages of this digital twin? So the advantages are the reduced development cost. You don't actually need to develop different systems to see how it will perform. You can just design a uh, basic system, a basic physical system, and then you can design its digital twin and do the rest of the experiments on that digital twin. Once you have the final outcome that you want from the analysis of your digital twin, then you can go ahead and design your physical system. So this reduces the cost because you are experimenting everything on a computer, and the model in your computer is exactly the same as your physical system. Okay, so it improves design through iterative simulations because at real time we're getting the data, and at every instant of time it is updating the model based on the physical system's health and the data. And it enables us for predictive maintenance. We can predict what's going to happen to our physical system, and we can provide solutions accordingly. Okay, so integrating digital twin with UAVs. Well, it enhances its capabilities by providing real-time system monitoring. We can enhance the decision making by integrating the artificial intelligence in digital twin and seeing how it performs. And then once the performance is good enough, we can go ahead and give that algorithm that we tested in digital twin to a physical system. Okay, so for example, here the picture represents a UAV system flying over a city, and it is giving you real-time data of itself and the city, and you can create a digital twin of the UAV itself, and as well as, if you want, of the city as well, based on the sensors that you are using. Okay, so precise simulation for mission plan. That's the capabilities. For example, we have some examples that how these capabilities can be used. Autonomous navigation in complex environments. We don't need to actually test our UAVs in complex environments. What we can do is we can use our digital twin, and we can give it complex trajectories, and we can see how it will perform. We don't need to actually send our system. We can we can see how the systems will perform in our computer using that digital twin. Okay, we can optimize the flight paths for better efficiencies. We can perform test fail-safe mechanisms, and we can do a lot of other experiments as well, right? So if, for example, if we were to follow a specific path among a lot of buildings of different terrains, so rather than sending the drone to the actual flight path, we can use optimization algorithms, and we can use AI techniques and see what is the best strategy to take this drone along this path. We can do all of this in a computer. And then once we have the finalized result that this is the best strategy, then we can implement it to our physical system. Okay. So if we talk about the application areas, uh, the first part would be the development and prototyping. How it is done is that we simulate the designs before physical testing. This reduces our development timelines because developing a physical prototype is quite complex, and it will require some cost as well, and time and effort and resources. If you have a digital twin, you can do a lot of stuff with without by saving time, cost, and effort, and manpower and resources. We can use it in operations and maintenance by doing predictive maintenance using real-time data. We can increase fleet reliability since we are getting real-time data and we're analyzing how it is behaving in real time. We can increase the reliability of the system since we already know what's going to happen. Yeah, and then we have this autonomous missions, which can be one of the potential applications for digital twins integrated with UAVs. That is simulated mission rehearsals. We can rehearse our missions. For example, NASA probably is not probably well actually using this digital twin technology for years, well, they simulate how it is going to be, how their spaceship or anything, any physical system is going to behave for a specific mission. So they do it again and again and again and again and see what could go wrong, what will happen, and based on actual physical system data from that actual physical system. So once they see how it is going to behave, they can optimize the decision-making algorithms and get to the best possible results in a computer. And once you have them, then you can go ahead and apply that to your physical system. Okay. So now we are going for a case study. So it's a lot of maths, but well, you don't need to worry about any of this. We're not going to the detail of what this math represents. I'll try to focus on the words that I'm saying. So then it will be much easier for you to grasp. So basically, this is a mathematical model that represents the motions of a quadcopter system. Okay. So just to indicate, well, this is a quadcopter system. Okay. A drone with 4 propellers. That's a quadcopter. Okay. So this was a quadcopter, a drone with 3 propellers, is tricopter, a drone with 2 propellers, is bicopter, and so on. So we're talking about this quadcopter system. Okay, you probably have seen this a lot of times here and there. So this is a quadcopter system. It has no wings. Okay, it has only 4 motors rotating propellers, and that provides a thrust, and it flies here and there. Okay, so this is the system that we're talking about. So this is a physical system. But if we want to like replicate it in computer, what we need is we need these mathematical equations. These are 6 equations: 1, 2, 3, 4, 5, and 6. So these are 6 equations that represents the motions of the quadcopter system. Okay. For example, this first equation represents the motion of the pitch angle of the quadcopter. Pitch angle is the forward and backward movement. So this first equation represents the forward and backward motion of the quadcopter system. The second equation represents the left and right motion of the quadcopter, which is called the roll. This third equation represents the yaw axis movement of the quadcopter system, the yaw angle, which is the quadcopter rotating clockwise or anti-clockwise, which is the heading, the facing of the quadcopter. It could turn left or right. Okay. So the XYZ are the XYZ coordinates, XY is the position, Z is the height. So these are all the possible motions of a quadcopter system. So we use these 6 equations to represent how our quadcopter behaves. We got these using laws of physics and some mathematical computational methods. We derived these equations. Okay, so these are second order differential equations. You see 2 double dots here, right? So this represents the second order time derivative. So we have 6 second order equations. Okay, we can convert 6 second order equations to 12 first order equations. Since these are 6 equations with second order, so first order would have 12 equations. So this is a state space model that exactly replicates the previous one, but it is a different representation. What's the point of this? We'll come to that in 1 to 2 minutes. But the point is, these are 2 different representations with the exact same meaning, and this represent the motions of the quadcopter system. So here we have some constants. For example, this factor kfax. This kfax is the aerodynamics friction constant. Okay. So if I have the smaller constant, it will have a different value of this kfa. If I have a bigger quadcopter, it will have a different value of this kfa. Similarly, for this kfay, kfaz, and then we have this kft as well. In x, y, and z, here you see this kft, which is the translation drag constant. So we have some constants in our mathematical equations and in our mathematical replica of our physical system. We have some constants. If we change some certain parameters, for example, if I increase the arm's length of my system, if I change the motor of my quadcopter system, if I do any change in my physical system, there are some constants whose values must be updated. How do we know what is the exact value of this KFA for the specific drone that I have in my hand, for example? Okay, I can't know it. I can just take a rough guess. I can say, like, yeah, well, normally the quadcopters that are of less than 2 kg, maybe with having a form factor of, like, let's say 10 by 10 inch, have the value of this KFA in like 10 raised per minus 5. I can just guess it. I can just provide a rough estimate of what would be the value of this, this physical system that I have in my hand. In digital twin, we can get the exact value. We can get the exact value of these constants, right? We don't need to guess it. If we change our physical quadcopter system, you understand that the quadcopter has 4 propellers. It could be small, it could be big. If it is smaller, it will have different values of some parameters. If it is bigger, it will have different values of some parameters. The overall mathematical model will remain the same. These equations will not change. The values of some constants will change if you change the size and other things of the quadcopter system. Okay, so let's say that we are not using digital twin. We are just going ahead and simulating the result. Well, in this way, what we will do is we approximate the values of these constants. Okay, we approximate the values of these constants. This is the example of a quadcopter system. Any type of physical systems, if it's from civil engineering, mechanical engineering, electrical engineering, biomedical engineering, or any type of physical system, it will have some parameters as well. Okay, so here the case study is for this quadcopter system. So once we have this random value of these constants, what we do is we just shifted these equations to another way. Here this G1, G2, G3 variables are the ones that represents this KFA, KFAT, and all of this and that. Okay, we just change the notations for a better and simpler word, because this is more complex and this is a bit simplified version. So these, we understand at the moment that for to design an intelligent strategy of a control algorithm that 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 makes our system to do what we want it to do, that ensures that our system is performing the way that we want it, we need to design a good control algorithm. And these constants G1, G2, G3, well, they have a major role in that control algorithms. Okay, if we give different or approximated or wrong values of these constants, our algorithm will not perform good for our specific physical system. Okay, so in these two slides, we understand one thing, that we have some mathematical equations that represent our system. These equations can be complex. We don't need to go to the detail of those complexities, but we understand that there are some constants for this. For example, this KFAX, this JR is also a constant, and some other parts as well. We do not know the exact value of these constants for this specific system that we have in our hand. We can take a rough estimate, we can guess it, but we don't know exact value. Okay, so these are the exact constant that we're talking about, this G1, G2, G3, G4, G5, G6, and so on. So there are some constants in mathematical models that we do not understand the value. We take a rough guess, and we use digital twin technology to take the exact value of our system that we have in our hand. So our problem of guessing the approximate value is solved by using the digital twin, because using the sensors and the data from our physical actual system, we upgrade these values. The question arises, what is the need of upgrading these values? Why not approximated values can do a good enough job? Okay, if this question arises in your mind, then to go for its answer, we need to see how our control algorithm works. Okay, so we understand the role of digital twin for now. Now we'll go ahead and see how the control algorithm works. Here you see some symbols indicating U2, U3, U4, and U1. There are three U1s, U2, U3, U4, and okay. So we need to design such exact values for these four constants U1, U2, U3, U4 for our quadcopter system to do what we want it to do. Okay, so we need some values for these four variables U1, U2, U3, U4. We use control engineering to get the values of these four variables. What are these four variables? U1, U2, U3, U4. These are defined using these equations, and ultimately they can be related to the physical system. This omega represents the speed of that propeller. You understand? We had a quadcopter and it had four propellers, right? So propeller was the rotary fan on the motor, right? You understand that? So the rotational speed, the RPM, the speed of that motor and that propeller, the rotor, right? The speed of that propeller is indicated by this omega, and to determine this speed omega of omega 1 indicates the propeller speed of motor 1, omega 2 for propeller speed of motor 2, 3, and 4. So to determine the propeller speed, we need the values of U1, U2, U3, and U4. Okay, so these were the variables that were in our original model. We need to design some mathematical equations to compute this U1, U2, U3, U4 in such a way that the system obeys us. Okay, so now we'll go ahead and design these U1, U2, U3, and U4. For now, to summarize again, we understood that there are some constants in our systems whose approximated values may give good results or may not. But if we use digital twins, we can go ahead and get some very accurate values of these constants. And on the other side, the second part of our summary includes how will we control our system. To control our systems, we have some variables in our system that we need to manage. For our quadcopter system, we had these four variables U1, U2, U3, U4. And these variables were related to the rotational speed, the RPM, the speed of the motors. Okay. Now we need to manage these four variables. That's the control part. First is the modeling part. Then second is the control part. We understood how modeling can be, how digital twin can be used for the modeling part. Now we're going to go ahead and see about this control part. Because we want our system to obey us. For our system to obey us, we need to design some intelligent control strategy to control and manage these four variables, U1, U2, U3, U4, which is managing the speed of the motors. Okay. So here is a complex technique, sliding mode control. Okay, you don't need to understand it. I'll just give you a very vague idea so you will understand some basic points. Okay, yeah, control algorithms work like that. So initially we saw that I told you that this first equation represents the forward and backward motion of the quadcopter, which is called the pitch angle. Okay, so this first equation was transformed into these two equations, these first order two equations. That was the second order single equation. We have now first order two equations. Okay, so this x1 and x2, these two equations represent the forward and backward motion of the quadcopter system. So we take this forward and backward motion for now. So these two equations, well, here we have, there we had this G1, G2, G3, G4. Now we have this Q3, Q2, Q4. These are the constants. Okay, any variable can be assigned. Now here we have this control part indicated by this U2. Okay, for controlling the forward and backward motion, we have this variable U2. How will we design it? The method is that we first introduce some errors. These errors are the value of our actual state and what we want our state to be at. The actual state is x1 and the reference value. This is the process. If anyone's interested, I'm happy to answer the details of how this sliding mode works. But since you probably don't have the background of this control engineering, I'm not going to the extra detail of this part. So I'll just go ahead and just give you a very vague idea. We define some errors, then we use another equation to represent a sliding surface, which is the core part of this control algorithm. And then we go ahead and do some manipulations and go ahead and do some more manipulations. And ultimately, we determine an expression for this U2. So this right hand side, this is the U2, and this right hand side, this whole equation, we use all of these symbols, all of these variables. We compute this mathematical equations and we determine the value of this U2. And then we feed it. Then we feed it to our original equation, and our system, our digital twin or our model in our computer gives you the motion. So you need to give some value to this U2 variable, and the value is calculated using this equation, this one. The variable is the value of this variable U2 is calculated using this equation. Why calculated using this specific equation? Because if we calculate the value of our U2 variable, we had the four variables U1, U2, U3, U4. We would took for the sake of analysis, we took this specific U2 variable for now. If we calculate the value of U2 using this specific equation, our system will do what we want it to do. It will ensure that if I say the quadcopter, the drone should go left, it will go left, because I gave it the signal go left. The system's command was calculated based on my command using this equation. Okay, so in this equation, you see that we had this G1, G2, G3 constants, and the variable names are changed here again. This V2, V3, this V1 and V2, these are the same. These are the same constants that we originally had, this KFAX, KFA1. So we understand the point of mentioning this control strategy was that in our control algorithm analysis, in designing the control algorithm, we are using these constant values of our systems. So if we approximate the values of our actual system, the constant values, it will affect our control algorithm as well. Here you can see in the control algorithm equation, those parameters are coming. If we use digital twin, to get an accurate representation of those parameters and a lot of other details of our actual system, it will make our control algorithm strategy more precise as well, more accurate as well. Our control strategy, the control theory, there is no flaw in this control algorithm. The flaw was that you were not giving it the correct information. The control algorithm will perfectly perform if you give it the correct information. How will we give it the correct information? By using the digital twin technology. Okay. Otherwise, you can just make rough guesses and we give it an approximate value, and it will try to balance the system, but may not perform very good. Okay. So this was some extra maths. That was the fundamental. I tried to show you how on fundamental level the digital twin affects the simulated model and the performance in that simulated model. Okay, so similarly, using the same methodology, we determine the values of other variables as well, U3, U4, U1. So U1, U2, U3, U4, these were the four variables that we tried to find the values so that it obeys us. So using the same methodology, this is a sliding mode control methodology, SMC short form, and we determine these equations. Okay, all of these equations are these constants, this V4 and V3. Oh, you get the approximate values using some generic methods, or you can get the exact value of the specific system that you have in your hand using digital twin technology. Okay, so once you have this U1, U2, U3, U4 values, you can go ahead and check what should be the RPM of your motor. Okay, so that's the case study. So now we understand the digital twin technology is really nice. We have any physical system and we use some sensors and we collect the data from this physical twin and we create a digital twin, and we can do a lot of a lot of analysis here, and we can, based on that analysis, we can upgrade our physical system as well. Okay, but the digital twin, well, it requires high computation requirements. You can't create a digital twin on your mobile phone or iPad or a basic laptop. You need good GPUs with high computational powers. Well, that's one of the limitations. Well, we need to integrate with legacy systems. It has some specific requirements. And we need to ensure that the data is accurately coming from our physical system. There is no inaccuracy in the data acquisition, and it is coming at real time, and it is synchronized with our physical system. And then we have the cybersecurity concerns as well, because we are getting the data from our physical systems. If someone hacks it, well, you may, well, it might be not very suitable to you, depending on the type of physical system that you have. So we have this cybersecurity concerns in implementing this digital twin technology. So if we talk about the future prospects, we understand that the main core part is getting the data from our physical system in real time. So we want minimum delays and maximum information. For that, we need to integrate our technology with 6G, 7G, and so on. So we need to get best possible communication protocols to get this digital twin perform at its optimal point, right? So we need AI-driven autonomous decision-making algorithms for the digital twin for higher and complex physical systems. And then we can use it for swarm intelligence for coordinated UAV missions, indicating that there are hundreds of UAVs. Probably you have seen some light shows in China. They create shapes in the sky at night. Well, those are the swarm UAV coordinated drones, right? So we can then go ahead and use it for cross-domain operations or air, land, and sea, and so on. So in conclusion, the digital twin technology revolutionizes the UAV capabilities by making it more robust, reliable, and controllable. It enables efficient, safe, and autonomous operations. It promises innovations across different kind of industries. It is not limited to UAVs. Digital twin can be applied to any type of physical systems. Digital twins are not just tools, but gateways to a smarter, more autonomous future. Okay, so that's pretty much it about our today's presentation. And if we have any questions, we can go ahead and take.
Thank you. Yes, he said, and if anyone has a question, you can use the hand reaction or leave a comment in the chat. So let's wait a couple of minutes so we can get questions. We had a question from Godwin. Let's see what he has to say. You need to unmute. I'm asking you to unmute.
Okay. Sorry. Sorry. Can you hear me now? Can you hear
Yes.
me now?
Yes, you are
Can you
audible.
hear me?
Yes.
Okay.
Yes.
Thanks for the presentation. It's an area that I'm involved in, aircraft design and maintenance. I will want to know the application for this digital twin for accident investigation. I don't know whether you are looking at it. It will be very nice for accident investigation. Presently, we use flight data recorders that acquire data. And once you have an aircraft going down, you have to look for those flight data recorders and voice recorders. So if we have a digital twin for an aircraft that is flying, you can actually pick what happened on that flight. I don't know if you can do light on that.
Exactly. Yeah. Of course. Of course. Yes, you can. Well, you have an aircraft. You created a model for it, and you used digital twin to synchronize that model with real-time performance of that aircraft. So, if there occurs a fault in that aircraft, you immediately see it in your digital twin, And then from there, you can use AI algorithms to predict what is going to happen to your aircraft in the next 1 minute. And to solve it, what is the best possible course of action that the pilot should take, or anything that should happen to that aircraft. You can use AI algorithms to get that decision within few seconds. And then yes, you can go ahead and take that try to take that action in physical, in real life. So yeah, the point of digital twin is this, that it is getting real time information from your actual system. So if there is a fault, it will immediately show you at your computer. And once it is at your computer, you can do a lot of analysis based on the AI algorithms.
Okay. My second question is this. Are you talking to aircraft manufacturers in this new vista, this new field? And if it's possible, you can elevate this to ICAO so that it will be very helpful for accident investigation. That's my question. Thank you very much.
Yeah. Yeah.
So I'd like
So
to have your,
basically, all of this.
I'd like to have
Yeah.
your details so that I can exchange messages with you. Thank you.
Yes, yes, sure, sure. I'll go ahead and share my details. So basically, all these manufacturers, once they have some prototypes ready. For example, DJI is a company that is selling the drones throughout the world. They have incorporated this digital twin technology to make their system very accurate and robust. So people around the industry who have physical reliable systems, they have already incorporated this digital twin technology, because it is one of the most important part for making your system reliable.
Yeah.
Yeah. I'll go ahead and share my email address in the chat box
Okay.
for any future references.
Okay, we have a question from CC Jules. Let's see what they have to say.
Thank you very much. Very, very great presentation. I thanks so much, Dr. Abdullah. So, okay. Now, my first question is, what material you use in the component selection phase? Aluminium, iron, silis, or what? This is the first question. I already put in the chat box my question to let everybody follow up. Okay. And second question, we can go question by question. Question one first to reply to answer, and after we go to the next.
Okay, so your first question is what material you use in component selection phase. Okay, so if you talk, well, this entirely depends on the system that you're going to work on. Okay, so in our digital twin model, we're not going to use any physical components. We're going to use physical components to build our physical system. So once the physical system is built, we'll represent that physical system using some equations. Okay, so if you use iron, we'll have some different parameters in our mathematical equation. Okay, so digital twin is independent of what your components are in real life. Question number 2, can you explain the autonomous process of the 3 unmanned equipment? By the way, how to explain the functionality that retains on UAV in air and UAV on water? Can you explain the autonomous process of the 3 unmanned equipment? I don't understand this 3 unmanned equipment word.
Yeah, because you talk about the UAV, aerial, the UGV first, ground, UAV, aerial, and the UWV, water. So for the ground, it's not very relevant for me. But how the system is retained? How the unmanned equipment, like the 2 aerial and water one, the first is written on the air, and the second, I don't know, for maybe the aircraft with the aerodynamical process, I don't know, and the UWV on the water, like the ships and so on. How to explain this functionality?
Yeah. So is your question is that if it is underwater, it's in ground, it's in air, how do we get its data?
Yes.
In digital twin?
What function retain on the air, for instance, the aircraft or the drone, And what system, what functionality can retain the equipment on water in the UWV system, for example? Just to know the functionality you can retain, to retain in the whatever in air or in water.
Okay, so I'm having difficulty in getting the point of retain.
Retain is
What's
like
the point of
to keep equipment in air and keep equipment on water. Instead to
okay.
Yeah.
So hovering, yeah, okay. So yeah, so the way it works is that we install some, for example, a position sensor on something that was airborne. Okay, so there was an aircraft in the air. We installed a distance sensor. It measured the distance from the ground, and it gave itself the values that you should maintain this distance. For example, it was 100-meter distance. So the sensor will keep giving it the values that you are at 100 meters, you are at 101 meters, you are at 99 meters. So it will adjust its values, and it will adjust its motor's RPMs or whatever it is controlling to ensure that it remains at those values. So again, we use some sensors to get the reading, and we take the actions accordingly. Okay. So your question
Okay,
3 and 4
for the third, yeah.
Okay.
Relevant constants. Yeah, the relevant constant.
XYZ means 3 dimensions, right? So XYZ are the space coordinates. X and Y are the position coordinates. Z is the height. These are the coordinates of the system. Yeah, the 3-dimensional. What are other variables in the formula? What are the value changes? G1, G2 have major role in UAV algorithm. So basically this KFT and multiplied with some other constant, we use G1 and V1 to represent those same values. So there are some constant values, some generic constant values for a generic quadcopter system, but to get the accurate value of the physical system that you have in your hand, you need digital twin. So as I'll use the case study to indicate that yes, indeed, they have a major role in the control algorithm, because these constants are being used to compute some equations that are being used in the control algorithm. So the next question is why we upgrade value. Once you have U1, U2, you can have the RPM. So we need to upgrade our values because at every instant of time, we want our system to do something else. For example, if our aircraft was like this and we wanted to move forward, we need to update the values of this U1, U2, U3 at every instant of time, because we're going to give it more and more commands. What does RPM mean? RPM means rotations per minute, okay, rounds per minute. And no inaccuracy in our real watch. Okay, so I don't understand the question 6. Question 7 is, does the UAV system use the neural network function deep learning related as I saw on the scheme challenges? Well, UAV can use neural networks, artificial neural networks, deep learning methods, and other stuff for designing the control algorithm. I gave you an example of a sliding mode control method. You could use a neural network method as well to design a control algorithm. But again, whatever method you use, it will use the mathematical model. It should be accurate, and digital twin makes it accurate.
Okay. Thanks so much for the answer. Thanks so much.
Okay.
Thanks.
We can answer 3 more questions from Olufemi. Let's see what he has to say.
Thank you very much. Professor Abdullah Mugies, please pardon me for joining the lecture rather late. My question goes first. Can you hear me?
Yes, you are audible.
Okay, please, my question goes first. In making some changes in the variables in the equations, maybe changes in the velocity u, or in the angular velocity omega, in making such changes or substituting some variables. Can you please explain what are the guidelines for maybe minimum or maximum limits for these changes? guidelines for minimum or maximum limits in making the changes. Also, if you have unfavorable weather, like some storm or tornado or whatever, are all this also to be considered in making such changes? Come back.
Okay, yes, that's a very good question. So basically, if we talk about, for example, the U1, U2, U3, U4, and we can talk about the limits that it may have, because the real values will come from the control algorithm. Okay, so the real values for these U1, U2, U3, 4, which are related to the rotational speed of the motors. Okay, the omegas, the U1, U2, U3, 4 are related to the angular speeds, the omega. So the control algorithm will tell what should be the RPM of that specific motor, omega 1, omega 2, omega 3, omega 4, based on what you gave it the command. For example, you said go forward. To make it go forward, motor 1 and 2 should be at a high RPM, and motor 3 and 4 should be at a lower RPM. At what specific RPM? The control algorithm will tell all of this to the system. Manually, humans don't do that. The purpose of control algorithm is to do this, right? So if we talk about the range and the limits, if you need to see your physical system and then apply these constraints in the control algorithm design. For example, if I had a motor and I saw that at maximum speed it can go up to 20,000 rpm and not more than that, I will apply these constraints to my omegas in my control algorithms while computation in those mathematical equations. I will tell it, if you compute anything above 20,000, for example, the control algorithm is saying omega 1 should be 30,000 rpm. It is not realistic. The maximum capacity of the motor is to go up to 20,000 rpm. So I'll put these constraints and they will limit it and provide a control decision accordingly, right? So other than that, no budget, no budget, no budget. So, sir, so the way it works is that in a tornado, the control algorithm will say the wind is so high, you need 70,000 rpm to cater that wind. If it's beyond the capacity of your physical system, which was the 20,000 maximum rpm, your drone will fall down. But if the control algorithm says that you need 15,000 rpm only, you need 15,000 rpm, it will survive in the tornado as well. So it entirely depends on your physical system's constraints. Theoretically, you will get all, there are no limits theoretically. You will get all bounds and you'll get all those values from the control algorithm. But physically, they might be unrealistic to implement.